So in this section, we are going to discuss a very important concept of organic chemistry, that is field effect. And I am taking this content, the examples from Jerry March. It is a very beautiful book of organic chemistry and one of the most bulky book in organic chemistry. That is Advanced Organic Chemistry by Jerry March. So field effect is a kind of inductive effect. Generally, in general organic chemistry, with inductive effect, it is being taught. So field effect, to discuss field effect, let's first take two observations. First observation is, let's take two molecules. Another benzene ring. Here Cl, Cl, H, H. This is the first one. And second one is quite similar. A 2-2-2 bridge with two benzene ring. And here the chlorine are in different direction. Chlorine, chlorine, hydrogen, hydrogen. And here C double bond O, double bond O, OH. Here also C double bond O, OH. Now these two molecules, experimentally, it is found that for the first molecule, pKa is 6.07 and second one, pKa is 5.07. That means which one is more basic? Second one is more, which one is more acidic? Second one is more acidic. So this proton is more acidic. Now, for the explanation, if we see inductive effect, then inductive effect will be similar. If we want to explain the basicity of conjugate base, then it will be conjugate base, and this one will be conjugate base. Now, if we want to observe the inductive effect of chlorine, then the number of bonds is same. And one more thing, the the chlorine is very much far apart to generate any such kind of inductive effect. So what things are stabilizing this? So basis, acidity B greater than A. Acidity. Acidity B greater than A. It is A, it is B. Now, what is the factor that is stabilizing that conjugate base of B, or what is the factor that is destabilizing the conjugate base of A? It is called actually field effect. Field effect means actually electronic effect. It is kind of electronic effect, not kind of steric effect. So electronic effect from space or through space. So electronic effect through space. What happens here? The chlorine, both the chlorine will have delta negative for this carbon chlorine bond, for this dipole moment. Here also delta negative for this dipole moment. And there is a repulsion, there is a electronic repulsion between this O minus and Cl minus, but the repulsion is through space. Rather, I would say it is not actually, it doesn't occur through space, because here we have water molecules, H2O molecules. So this Cl minus polarize one water molecule, this polarize one water molecule, this polarize another water molecule, and a chain of polarization is generated. And this, through this chain of polarization, this negative charge repulsion reaches to this O minus repulsion. So their repulsion is not through 100% space, but through the chain of water molecules inside them. So for this, the first one, the first conjugate base, that is conjugate base of A, will be less stable, and that's why it is less acidic. So conjugate base of A is less stable. So this is field effect, and this field effect is a kind of electronic effect, but the difference with other electronic effect is here geometry or orientation, geometry or orientation of groups important. But other for other electronic effect, for example inductive effect or resonance, you would not see any effect of such kind of geometry. So this is the basic difference with the other electronic effect. That is, it is geometry or orientation dependent, because orientation creates the difference between the distance in the field. So this is a kind of very popular example of field effect, but it is not the only one. There are very uh, important. There are some very important aspects in different field of chemistry where we can see this type of field effect. For example, uh, if I tell you, this is also very popular question of ethylene glycol. If I tell you the ethylene glycol, if I ask you the ethylene glycol, what will be its most stable conformer, then you should answer it will be Gauch will be more stable, because in Gauch conformation there will be one hydrogen bond of ethylene glycol, right? But uh, if I tell you that if we want to compare the the Gauge or anti, the conformational stability in aqueous medium, what happens? Gauge, if we want to compare the Gauge versus anti, in aqueous medium anti will be major, Gauge will not be major. OH in aqueous medium, Gauge will not be major, because this hydrogen bond will not be there. So what will happen? This H is connected to water, and many water molecules will be trapped inside this. And due to this, kind of this the interaction of hydrogen and oxygen, which initially generated the hydrogen bond, this will be disrupted. So this is a kind of field effect, and due to this field effect, the hydrogen bond interaction is disrupted. That's why antiform is major. This kind of system, another kind of system, you can see, for example, a molecule having C double bond O minus, and here NH3 plus. If we want to draw the conformer of this molecule, then we will have C double O minus and NH4 plus. For this also, a Gauge form is more stable than anti. Why? Because this electronic interaction, but there is no no sigma bond or something inside them. So what happens? This electronic interaction occurs through space. So this is a kind of field effect. That's why here Gauge conformation is more stable. So this is a concept of field effect. Hope you have understood it.